All right. So I mentioned this earlier, so I dropped the name earlier, and it's in your book as well. In Real Stuff 3.7 talks about streaming SimD. So they give a very specific example of. Did I do something funny? He's laughing.
His phone went off.
Oh, did it?
Yeah.
Oh, is that the
Siri or whatever he has?
Oh, I heard. The sound. I gotcha. Did I set it off?
No, I don't think so. What is that?
This?
Yeah.
That's a good question. I found it. I found it on my my cable box.
What?
Like a box cutter, or
No, I think it's like a golf bracelet, like a magnetic, like one of these like magnetic, balance your yin and yang or something like that. So I think I had it from a long time ago, and I just had forgotten it even existed. And I happened to be cleaning our dresser thing that's in our living room where I keep my laptop and all my junk, and I found it on top of the cable box. I just put it on, and
Just kept it off.
oh, Mr. Gonzalez was wearing your bracelet. Yeah.
Oh,
He got me like in this Indian friendship bracelet.
what happened to the Indian food that's gonna like destroy me? The last.
I went out. I had Indian food with them the other day. It was pretty good.
Next week I'll plan.
Yeah.
Last week I have already planned, but the class was just planned.
Oh, I gotcha. But then he abandoned me at the restaurant.
No.
I'm sitting there. He just leaves. True story.
Stuck with the bill.
Yeah. No, I wasn't. But the waitress comes over. She's like, you should go now. I think he's gone.
She wasn't meant in that way. She said he was gone. He will come back in a couple of minutes. Just to wait.
Oh, I like ask.
Her English was like that.
So her English is crap.
Very crap.
So, I mean, we're talking like old Alex.
Whoa. Father up.
On a scale of old Alex to Blade.
There's not much variation.
Well, Blade speaks pretty good.
The scale of old Alex to Blade versus just talking to a shoe.
Blade has some great phrases that he uses sometimes. Like the time that he almost like hit somebody in a car because they were driving stupid.
Yeah.
He pulls it next to him. He's like,
Wait, what? He got in a car.
No. Like we were driving to breakfast one morning, and somebody in front of us, like the light was green, but they were letting somebody cross because it was Saturday morning and no one really cared. And Blade's just like, what is this that they're doing? So like we pulled up like next to him because we were turning later, and he's just like, I want to see if it's an African American brother. Because of how he drives. I'm just like, it's 7 a.m. on a Saturday. I'm just like, what?
I remember you telling me that after you showed up. Oh, yeah. All right. So in any case, in 3.7 in the book, they talk about a specific example of SimD. I'm not going to go too far into that because we're actually starting chapter 4 here in a second. So your homework assignment for next week, we're going to actually have 2 parts of the assignment. One is going to be to answer some questions from the end of chapter 3. I'm going to design it to be maybe like an hour or so worth of work. There's a lot of questions. I need to look at them closer to see which ones are like conversion. Because the other assignment is going to be the research stuff that I'm going to talk about here in a little bit. So, because we have to propose a topic and that kind of crap. All right, but let's kind of wrap up chapter 3 by talking about SimD just a little bit at a high level. We kind of spent the first part of class today stumbling into SimD. I had to guide it a little bit, but we kind of stumbled into this guy. So really, SimD is this, stands for single instruction, multiple data. So we just gave an example of this guy where we had a single thing we wanted to do. We wanted to dim pixels, right? Dim a pixel. Now, we wanted that to be done across a big matrix of pixels, multiple data points. Make sense? We have a single thing we want to do across multiple data points. That's what SimD does. All right, so SIMD is all about taking micro machines. Okay, so that's just more my phrase. Actually, it's a phrase from my childhood. They used to have these little cars. They were called micro machines.
Yeah, they had those.
They still exist?
Yeah.
All right.
I mean, they might not exist now, but I remember
No.
those when I was
Yeah.
a kid.
But in any case, so taking a very simple circuit that doesn't do that much, doesn't have a lot of logic associated with it. It's not the antithesis to a general purpose CPU. So something very simple, and then duplicating it a bunch of times to perform some important but relatively mundane task in parallel. Make sense? Dimming an entire screen. Let's see what kind of examples they give. Adjusting the contrast in a digital image, adjusting the volume for digital audio. Yeah, here they're talking about individual pixels, that kind of stuff. So, we're kind of, this stumbles us into this idea of disadvantages. So kind of finishing up the discussion of pros and cons as it relates to this type of parallelism. Not every problem will conveniently fit into something that is solvable in this way. They say it's not easily vectorized. We can't divide up the problem into a single task. We want to do this across all of these data points. Not all problems, actually probably very few problems in terms of a percentage, lend themselves to that type of thing. Make sense? But we can do this in hardware because it's fast. So every now and then it's a major benefit if we decide to use it when it's the right tool for the job. Why wouldn't we do this in software? What's the problem with trying to emulate SIMD in software?
You only really have one or maybe 4 instructions that you can execute at a single time now.
Okay.
So you're still bottlenecked by however many executions you can make at a single time. But in hardware, you can theoretically do them all at the same time.
Provided you have room and heat dissipation, right?
Yeah.
Yeah, so like we were talking earlier about there like being a monitor with the correct kind of microcircuits in there to do this job. Monitors know how to adjust the brightness of themselves if told, right? You tell a monitor to reduce brightness by 15%, the monitor magically does it. Okay, so these things have that built in. They have the right kind of ventilation and stuff like that to dissipate the heat, and the real estate for having all those things on a per pixel basis is there. Now that doesn't mean that you have to have the space, like the size of the screen where behind each one's a little circuit. You could still have a circuit board that just is massively parallel, where it has a little cluster in the circuit board that literally does something either once per pixel, or the reality is, especially with high resolution monitors today, you probably wouldn't adjust brightness or contrast or something like that on a per pixel basis. You would do it on a per section of the monitor basis. So it's like kind of a halvesy solution. So we said at the very beginning, well, near the end of before our last break, that if we did this literally on a per pixel basis, not SIMD, just you go brighter, you go brighter, you go brighter, then you'd see the sweep motion, right? Assuming that the processing unit wasn't so quick that our eyes would be deceived. But the punchline is we would probably see kind of the wave effect go across. Well, can we meet ourselves kind of halfway and say, you know what? And this is where I was going with, if each of us go out and we're in charge of 500 votes or something like that, 500 voters, could we have one simple machine in charge of 500 pixels? Another one in charge of 500 pixels. Do we feel that because it's hardware and the speed of hardware, that can happen quick enough, even if it's not happening in parallel within that little chunk, that if we have 100 things doing 500 things each in parallel, that we would be faked out to think it was happening in real time. Somewhere in there's a balance that we feel that's probably a legit approach. So typically, SIMD doesn't take it down to the granular level of, for example, per pixel, but it would take it down to a more granular level of then, just do, sweep through and do one thing at a time. So not all algorithms are easily vectorized, so not everything's a good fit for this. Well, some of these are not going to really apply to this, so let's actually forget about what their list is. Any other disadvantages you can come up with related to SIMD? There's clear advantages when we have a problem that lends itself to it.
Well, that's the thing, is you have to have a problem that lends itself to it.
Okay, but is there let's say we do have a problem that lends itself to it. So let's stick with our dimming example. Is there a disadvantage to SIMD for that?
The instruction has to be the same. You can have one go to 15 and one go to 30.
Well, okay, but then it's no longer SIMD.
Right.
I mean, SIMD is single instruction, but I get what you're saying. So that kind of falls back into the category of identifying a problem that's solvable with SIMD. So we've identified we have a problem. SIMD is a good fit for it. What are some concerns related to SIMD, or what's a concern related to SIMD if we're going to use it for? Let's just use our dimming example. You've probably seen this happen before, or at least heard of it happening before. As it relates to monitors, have you ever had like a section of the monitor go out? Like there's a section of your monitor that's dim? I have an iMac, an older iMac, that half the screen is substantially darker than the other half of the screen. Because they actually implemented the hardware-based, I'm just going to call it SIMD. It was actually an older version of that. But they implemented it as kind of a hierarchical approach. So I think the screen is handled in two halves. So there's a top-level circuit for each of those two halves. And then underneath that top-level circuit, I think, is in charge of 4 quadrants in that half. And then each of those 4 circuits are in charge of, various sections. So the top-level circuit on one of the halves had a problem. Okay, and because of that entire side doesn't its brightness is a constant. At least it's on, right? So it's just always kind of like a mid-range brightness. There's no adjusting it on that side. So kind of a interesting thing. Just you can almost experience it. Have any of you ever had an issue like with a monitor where like strangely a whole section of the screen has a certain behavior? Some older TVs, you might have the thing. This is would be related to SIMD, but it's kind of a precursor, if you will, where you'd have every other. A lot of the monitors were divided into like ribbons, so you'd have like every other ribbon. Maybe it was maybe 30 pixels tall, something like that, would be dead. So you would have your picture would look like a flag. The American flag with stripes, but you'd only see every other stripe. So kind of an interesting thing. So kind of the idea of SIMD comes down to the whole idea of data level parallelism. So rather than looking at parallelism from a problem perspective, we're looking at the ultimate endpoint, the data we want to manipulate, a pixel in this case, and saying how can we do a whole bunch of these at one time? All right, we take it to detasseling corn. We have a whole bunch of corn stalks that each have a tassel on. We want to get that tassel off. Well, if you have 5,000 corn stalks, you can get 5,000 people, or you can get 2,500 people and put them each in charge of 2 stalks, so on and so forth. Right? We can decide what's the efficiency of it. Where typically, any of you ever do corn? Cursor, you probably did corn detasseling, right? Not in, really?
No,
You're in Indiana.
I worked with my dad all summer.
So you never did corn to test? I mean, it's got to be a big thing where you're from, though.
Yeah, no, I did.
Okay.
Fast time. Yeah, fast
No,
time.
it definitely is. You get on the little machine and just
Yeah.
start picking away.
Yep. So that was kind of a real life example of that type of thing.
It's actually why he came to Wisconsin for school. They shunned him.
They
because
shunned
he
him.
used to shuck corn.
It's not shucking corn. It's removing the tassel. Shucking is different.
Big difference. And they only detassel one. They only detassel 3/4 of the rows.
Yeah.
Being from Indiana, you know that.
Like, you seem to know a whole lot about this for never doing it. It's like the exact same question that went in during his recent interview.
What?
I'll let it process for a second, see if you guys get it.
Oh, of course.
All right. So let's start talking about some digital circuit stuff. And then we're going to kind of drag these two things together. So think about digital circuits kind of like Legos. All right, so these are our various hardware things. You never actually see them like this because when we think about when you open up a computer, you know, if you crack open your phone, you're not going to see a whole bunch of wires and stuff like that in there. What are you going to see? You're going to see a printed circuit board, right? So on that circuit board, you have a zillion of these things all printed in there. All right, but these are our normal logic gates. When we talk about computer programming, we talk about the way we solve problems is through memory, asking questions, and repetition. Well, memory we do for computer programs. We do, well, human beings use their memory. Computer programs emulate that through variables. Hardware emulates that through wired memory to remember pieces of information, bit streams across a period of time. Now, secondly, human beings ask questions. Computer programs do that through conditionals. And part of what conditionals require are Boolean expressions. So these are our Boolean logic gates that allow us to, at the hardware level, ask questions. All right? So we want to be able to identify these guys. So we can call these guys our hardware primitive types. So the AND looks like an extended D. Okay? It takes in two inputs. So this guy is a function that has two inputs and it has one output. Now the output of an AND is true, on, if both inputs are true. Both inputs are on. Okay? So, and we have a truth table for these guys somewhere in here. Is it up higher? Oh, well, here, we'll go with this. So here's AND. So 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. All right? So that's our AND, and that's the way it looks. Here's our OR. Looks kind of like a little arrow. Two inputs. This guy is true whenever there is at least one true input. So this function, this OR function, takes in two inputs, has one output. It's only false when both inputs are false. So 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. Make sense? Then we have an inverter or a NOT gate. This guy takes one input and has one output, and the output is the inverse of the input. So this guy is depicted with this little circle. So this says take the inverse. Okay? So 0 becomes a 1, 1 becomes a 0. That's an inverter. All right, so then we take that lesson of the inverter thing and we say, okay, well now we can have things like NAND gates. That is not AND. So here's a normal AND gate with the little NOT guy on the other side. So he flips the answer that would normally come out of an AND gate, or come out of an AND gate. So this guy will be true under every single circumstance other than when both are on. So it's the inverse of an AND. So 0 NAND 0 is 1. 0 NAND 1 is 1. 1 NAND 0 is 1. 1 NAND 1 is 0. Another Lego. Somebody score?
This is loaded.
Loaded one out. Subs.
What inning?
Third.
And what's the score?
3-0.
Oh, 3-0 still. And the Cubs They're the ones with the bases loaded, or the Cubs are pitching?
Yeah, I think Cleveland's switching pitchers.
Calling in a wild thing? All right. So that's a NAND gate. So another one of our primitive type gates. NOR gate looks like an OR gate with the little circle thing there. So that's not OR. This guy is true only when both inputs are off, false otherwise. Nobody writes exclusive OR like that. Nobody says EXOR. It's just XOR. So this is the only thing.
Look on the monitor. Has the E kind of cut off?
Yeah.
Where is this?
For us. There's no E for us. 'Cause look.
Oh, I see. Yeah, good. I did that on purpose. It's by design.
At least the
Intelligent design?
Simdi. Yeah, intelligent design. Christian worldview. All right. So, where am I at here? Exclusive OR. So exclusive OR looks like an OR with a little curvy thing here in the back. That's the exclusive symbol, if you will. So we're kind of learning the nomenclature for this. So that's the exclusive symbol. So it's a normal OR, but exclusive OR says one or the other, but not both. So it's at most one input is a 1. So 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is a 0. Too many positives there for an exclusive OR. So this is the difference down here. Make sense? What happened now?
Too many positives. I'm just like an STD test.
Yeah. Exclusive NOR should not exist. Nobody uses this. Nobody uses exclusive NOR. Actually, like I said a few minutes ago, nobody uses any of this anymore. This would be strictly for prototypes. Because now it's all printed circuit boards. You know, nobody sits there with AND gates and just starts soldering crap together anymore.
Don't they only use NAND anyway?
Well, that's
In
they
not-
either use let's see, it's NAND gates or inverters with XOR gates. Because you can build any of the other gates with just those, and they can buy those in bulk.
Yeah.
And since you can buy those in bulk, it's cheaper for your prototypes. Yeah. So rather than having all these, but that just becomes an economy thing. You know, you'd be better off using the right tool for the job when you're making your. But if you're a company that's making these really complex prototypes, then you need millions of these circuits, and then it becomes a cost thing. So exclusive NOR is something that shouldn't exist, so we're not even going to talk about it. All right, so this is kind of our chart here. So everything except this exclusive NOR is a thing. So these would be our primitives for logic gates. All right, that makes some sense. Who?
Grand Slam.
Grand
Cubs.
Slam.
Really?
Yeah.
7-0.
Addison Russell just hit a bomb to dead center.
Oh man, Chicago's gonna be wild.
Man, it's going to be awesome when they still lose this game. How do I compete with this? I'm up here talking about AND gates. Got my students live streaming the World Series. This is garbage.
One of my coworkers is like T-ball. That's all this is.
Oh, it is T-ball?
T-ball.
All right. So think about these as our primitive types for designing circuits. Make some sense? All right. Now, let's introduce one less primitive. Let's look at a half adder. All right. I like the Wikipedia pages. They usually have good pictures.
Wow, even moving diagrams.
Yeah, look at that. Oh, except I don't want to show you that one yet. Okay, and you're not allowed to look at Wikipedia.
Watch the game.
Well, no, I want to break this apart and have us create a scenario with those primitives, right? So don't look at Wikipedia. It'll hurt the exercise here. All right, so we have this idea of a full adder and a half adder. Have we heard of both of those things before? What's the difference? What's the difference between a half adder and a full adder? Grand Slam Cubs!
I was gonna say an adder is a snake, but I don't know about a half adder.
When you take the snake and you just
Cut it in
cut
half.
it in half.
As it relates to circuits, this guy is a half adder. There's its cousin would be a full adder. What's the difference between them?
In that instance, your parents, siblings, child.
Most of you should know the answer to this. If your undergrad wasn't in computer science, you might not, but the rest of you should probably know this.
Off the hook.
Well, okay, let's start with this. When I say we have a circuit called an adder, what do you think an adder probably does? Adds crap, right? So, it adds stuff. Now, all the things we've looked at so far have been single inputs, or well, two inputs. So like an input into an OR would be two inputs, one output, right? So we think about the OR like a function. Now, those inputs that are coming into the OR, I've advertised as being like just zeros and ones, right? Realistically, it's an electrical signal, but we don't need to think about that. This is an electrical horse. This is, we want to think about the logic of it. All right, so the input to an OR would be a 0 or a 1 and another 0 or a 1. The output would be the OR logic applied to that. The input, here A and B, these would be zeros or ones coming into this. So when you add a 0 or a 1 to a 0 or a 1, what are your possible outputs? All right, here, we'll make it simple. 0 plus 0 is what? 0. Good. Okay. 0 plus 1 is what? 1. Good. So far, 2 for 2. 1 plus 0 is?
Grand Slam Cubs.
1 plus 0 is 1. 1 plus 1 is 0 with a carry. 0 with a carry. Okay? So, half adders have two inputs. You come into the two inputs and, this already sort of gets kind of what, that's an exclusive OR, right? So, this is an OR. This is the XOR, the exclusive part of it. So that's your output. Now your input, this guy is the output for your carry. Okay? So now, with me so far? This is a half adder. Half adder adds two 1-bit values, producing a result. The result will be the answer plus whether or not there's a carry. This guy will always be 0 or 1. This guy will always be 0 or 1. What's a full adder? What?
Does it input carry as well?
Yeah, full adder takes 3 inputs. Takes 2 bits and a potential carry. Make sense? All right. So, without looking at any online material,
I'm not worried.
besides the Cubs.
Did you want you're watching like a weird feed thing? Did you want the link to that stream?
Everyone should leave their laptops when I want to get a behind the class picture.
We'll make it full screen.
I will open it this
This when your class competes with the World Series.
Let's go straight to Facebook.
Straight to Facebook.
No, that was a text to Dr. Lackler.
I expected that. Oh man.
See, I'm interested. Like it's off hours. I'm interested to see what his reaction is.
Yeah,
He'll reply.
I'm interested to what his reaction will be.
Oh, he'll laugh.
Now the day we had lunch, he said, I'll bring some fire extinguishers.
Oh, that's right. Yeah. Well, he would need more than that because he's allergic to chicken.
What?
He's allergic to chicken?
Yeah,
Really?
Dr. Locklear has a chicken allergy.
Like,
Anybody
what
else?
about it? Like,
I don't know. Must be something in the protein or something like that. Yeah, so it's.
It's gonna be rough.
I mean, I don't think it's like new. And he's quite old, so he's learned how to adapt.
You just go straight vegan.
No,
you can't eat chicken.
Beef.
There's definitely a lot of other
No,
good meats. you can
chicken
still
is
have.
the only meat.
I don't think that's even true.
Bacon? Bacon.
Yeah,
Like
bacon.
Bacon.
All right, so here I'm gonna pause the recording. Well, I'll pause it in a second. So what I want you to do is break and see one. Let's do what groups do we want to have?
This is really complicated. Sometimes it's just.
And you're really having a hard time with it.
You're with Shiva.
Okay.
Old Alex. You're with Tim.
So literally last.
Is that's the same group we had? Yeah, well, you guys are sitting in the same place. Then let's do 3 of you. Based on our primitives here, so I'll leave it up on the screen so you can see it. Not that guy. This guy. Create for me a full adder. Do you want Paxton to refresh your memory about what a full adder is compared to a half adder? And don't look it up. I want you to use your logic. I've left your primitive types up here. So leave your Cubs game on or whatever, and draw a diagram for a full adder.
Yeah.
Who has paper? No one has paper.
Hey, don't use paper. I have a website.
No one has paper.
Hmm.
I don't watch it often.
That's the thing. I gotta keep drinking. I've been drunk for like 20 years. If I stop now, the hangover's gonna kill me.
All right. So we want to create a full adder. All right, so full adders are going to have 3 inputs. A, B, and a carry. Okay. So, what do our circuits look like here? That's pretty involved. Is that the easiest full adder?
I think so.
Could be.
It works.
Probably not the way you said that.
All right, so let's look at a truth table here. So full adder has 3 inputs, right? So we have 1. Actually, let's do 0, 0, 0. It's going to have 2 outputs, right? What's the 2 outputs? It's going to be 0 with a 0. All right. Then we have 1, 0, 0. 1 plus 0 is 1 with 0 the output. Then we have, actually, let's do this. Let's be more, we're going to do it that way. Yeah, we'll count up. So let's do it that way. So, it will be, yeah. So, if we have a carry, so this is 0, 0, carry. So 0 plus 0 plus 1 is 1 with no carry. Then we have 0, 1, 0 as our input, which is also going to be 1 with no carry. Then we have 1, well, I'm sorry, 0, 1, 1, which is going to be 0 with a carry. Then we have 1, 0, 0, which is going to be 1 with no carry. Then we have 1, 0, 1, which is going to be 0 with a carry. Then we have 1, 1, 1, which is going to be 1 with a carry.
1 1 0.
Oh, did I?
You missed one.
Oh, thank you. 1 1 0 is going to be. I haven't missed 2, did I?
7. No, there's gonna be 8. You'll have your 8th one after this.
Yeah. So 1 1 0 is going to be 0, carry the 1, and then we have 1 1 1, which will be 1 with a 1 carry. So that's our truth table for that guy, right? Okay. So we have 3 inputs, and we need the outputs to look like this. How did you go about solving this problem? We had to solve it in terms of our primitive types that we had. Now, a half adder was pretty simple, right? Exclusive OR, blah, blah, blah. Not a whole lot to it. Why is a full adder so much more difficult? So let's just look at the first 2 bits first. We can handle A and B as a single input, right? Well, as just a normal adder for that. Because this guy, this carry bit, is going to potentially have a side effect to it, right? So 0 0 gives us a. How do I want to ask this without being able to? Let me look at your website to see if. Does it let me draw lots of things at once?
Yeah, you can draw a lot.
You just can't test them.
You
Okay.
can't have 2 outputs. You can test one at a time.
What do you mean I can't have 2 outputs?
Like
You
it gives
can't-
you one output box to point to, so you just have to switch like which side you're
You're
looking at.
Oh,
the
yeah, I don't-
number or the carry.
I'm
Yeah,
sure there's better ones.
I don't like that.
They're
So,
probably
We'll do it this way.
he didn't look that hard.
Let's move this out of the way for a second. Alright. Alright, so let's start at the top. What is your, did you still use an XOR for your top? Alright, so coming into this first,
7 1.
They scored. No shutout.
is this got a push notification?
I think that's what that was.
Alright, so we have our inputs coming into this guy. Alright, so when A is 0 and B is 0, our final output over here should be 0. So if we're going to do this for this XOR, so this is the direct output of this guy right here, right? So let's create, I'm going to left justify this. So truth table for XOR is 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So that's our truth table for our exclusive OR, right? So let's look here, 0, 0. Our output is 0. We're good there. Here's 0, 1. Our output is 1. We're good there. Here's 1, 0. Our output is 1. We're good there. And here's 1, 1. Our output is 0. We're good there. So does this already handle our correct output for these 2 inputs? Okay. So we'll draw a little line coming off this guy. All right, and we'll go ahead and we'll throw that little truth table over there. All right, well now we have this carry bit that flies into this. All right, so we're going to need another gate here. Now realistically, this guy is going to feed into this as an input. And then this guy is going to feed into this as an input, right? Okay, so our inputs here are going to be the outputs of this guy as well as whatever the carry bit's going to be. So we have, let's steal this guy here. So what we want here is a 0. Well, here, let's go this route. This guy up here, is he, I want to ask this. All right, we'll keep it. We're going to feed in our inputs here. So our possible input's going to look just like this truth table, right? But this is for an adder. All right, well, I guess a half adder sort of, since we just have 2 inputs. So if we have a 0 here and we have a 0 here, the carry would be a 0, right? If we have a 0 here and a 1 here for our old carry, what should the output be? What's this guy down here trying to calculate?
The value at that position. So it should be it should be what gets it.
That should be the final value.
Final value.
Yeah, so it should be.
Okay. So when we add 3 bits, we have to add 2 bits and then we throw the other one in there. So this is like a second adder, correct? All right, so we have a solution from our first 2 bits that feeds into this guy here along with this. And now so should this guy also be an XOR? All right, so this guy is going to have an output coming off of it. And the output of XOR looks like that. Okay. And is that our correct? Is that our correct answer? If we had a 0, well, our correct answer for the top, not the carry. So if we had a 0, 0, 0 come in here, so that's 0, 0, 0. 0 XOR 0 is going to be a 0. 0 XOR 0 is going to be a 0. So we're at a 0, so that's 0 across the boards. We're right there. Well, we haven't actually had our output for the carry yet here. Then we have 0, 0, 1. So this is going to still be a 0 coming out of here. We're going to have a 1 coming out of here. So 0 XOR 1 is a 1. So 0, 1 is a 1. We're good there. Then we have 0, 1, 0. 0, 1 is going to be a 1. 0 is also going to give us so this is 1 and 0, going to give us a 1. Then we have, 0, 1, 1. 0, 1, 1. So this is going to be a 1 coming out of this top one. This is going to be a 1 coming in here. 1 XOR 1 is going to be a 0. Right? So 1, 1 is a 0. We're good there. 1, 0, 0. So we have a 1. Then a 0. So that's going to be a 1 coming out of there. Then a 0. 1, 0 is a 1. Looks right. So is this always going to be our correct output? All right, so we're good with our correct output there. Where does our carry come from?
Magic.
You have to know whether it's if A and B are both 1, and then C is 1 as well. Or A and B are 1, or C is 1.
We gotta take the result.
Oh, you gotta take the result from that one as well.
Okay, so here are our carry bits, right? So carries are 1 under these 4 circumstances. When our input was 0, 1, 1, when our input was 1, 0, 1, when our input was 1, 1, 0, and when our input was 1, 1, 1. How do we calculate that carry? What's the simplest way of calculating that carry? We can use You want an AND gate? Okay. So there's our AND gate. What are we going to do with this AND gate?
The first XOR output, if it is 1, and carry bit also 1, then we push the output to 1. And then we need another gate to process the 1 also.
It'd be the AND gate, what gets put into it is A and B, or the result from that first XOR, and then the carry, whatever carry input is.
Okay.
So the result from the first XOR, if it's 1 and the carry is 1, that goes into,
Well, there's no if. It just goes
Yeah.
into it.
All right. So the output of this first XOR becomes an input into both this XOR and this AND.
Yep.
And this carry provides both the input to this XOR and this AND. And
then there's another AND,
okay. What's the other AND going to be?
A and B.
Okay. Why?
So what that does is it checks if A and B are both 1, it'll send it to another OR. If that AND was 1, or that the one that we just created right there is 1, then the carry is going to be set to 1. So if one or the other are 1, the carry is going to be 1.
Okay. Let me simplify something here. I'm going to create a little truth table that just involves the carry bit. So carry is going to be, let's see, for output we're going to have make sure we're calculating this the right way. That's our carry. Two bits, so this is our first carry. Okay. So 0, 0, 0, 1, okay. So when we have an output of 0 from our original XOR, so that's going to be let's simplify this, get you in the right direction. What I want to do is I want to draw you a small truth table given the inputs of an XOR and the input of this carry into an AND, producing the results. Possible inputs could be this, where the only one would be that.
So that's an and.
Yeah.
Oh, wait. We're overcomplicating. Oh.
You are overcomplicating it.
It's literally you just have another half adder from C and the result of the XOR, and then you have yeah.
That sounds like you're making it more complicated.
Carries.
Or the 2 half ladders.
All right, so you're going to have a full adder is implemented in terms of
2 half adders.
2 half adders.
Yeah.
All right, that's fair enough. Okay. Can we? Well, so let's write this the way that you solved it with too many circuits, and then we'll see where we can simplify. Let's go that route. So you have an AND, and you said you filtered this into another AND.
No, we had an AND from A and B, or A and B was an AND. The one that we have there is an and then you OR that, and that's the answer.
Okay, so you had this guy coming into an AND. You had this guy coming into an AND. You had its solution, and you fed the solution into an OR.
Yep.
And then the answer off of this was your carry.
Yep.
So this guy here is C. This guy here is,
Answer.
yeah, answer. Okay. So here we'll take these guys out of the way for right now. Can that be simplified? What does a full adder, or I'm sorry, what does a half adder look like?
Just get rid of the exclusive OR off the other one, and then get rid of the and off the other one, and then the OR doesn't exist, and that's it.
All right, so let's flip it over. Oh. So half adder is not going to have the C input. Let me just dump.
Oh, that
Like-
not.
All right, so what does the half adder look like?
And then you just have A and B and
I mean, that has the same amount of gates. It's the exact
No, just
right.
play along. We're good. All right, so half adder has both these guys going into an XOR. Okay, which produces our answer.
The only case we need to consider for the carry when both are ones. So we need an AND gate.
Okay, so you want an AND gate? Because that sounds like a carry, right? Only when both are ones?
Yeah.
All right, so we have an AND here.
For the both inputs.
And feed both of those guys into that. Okay. So that's a half adder. Okay. So you have that sitting in front of you. Now you mentioned you could implement a full adder in terms of two half adders.
That's what we did.
This is,
That's like literally what we did.
no, hold on. How can it be simplified? Does a full adder require two half adders?
Because there is a third variable.
Say this again.
There is a third input variable like C. So we're gonna need the outputs of half adder, give it to another half adder, and make a OR decision at the end with respect to that third variable, which will be 1, 1, 1 resulted to all the cases.
So when we did this math over here, when you're taking your three inputs, we take 0 plus 0 plus 0. We're adding three things, right? We're adding the first two, getting the result, and getting the last thing. So this feels like it's one half adder. This feels like it's a second half adder, right? My question is can that be made more efficient? Do you need two half adders to implement a single full adder? Or is there a trick?
I'm guessing there's a trick because you're pushing us towards that. Or you're just trying to make us think about it.
Well, I mean, if you want me to really confuse it, then we'll go back and say, well, earlier you said something about, well, couldn't we just buy, doesn't a company just buy a zillion NAND gates and just use those NAND gates for everything, seeing as though that you could buy those in bulk less expensively than having a bunch of OR gates and AND gates and all those things. So why not just buy a whole bunch of half adders and just do everything with those? Like, why buy an adder if you know? Why have a special order for an adder if you can just have a zillion half adders laying around? And so if we're calling this guy, so let's abstract this.
You can do the can, but it's the same amount of gates.
Let's abstract this. We're going to say that this guy is a half adder.
That shit's more.
Okay. All right, so here's our abstraction of this guy up here. This is our half adder with our two outputs. How do you want to put this half adder with a second half adder to make a full adder? You want to have your carry bit wired as an input into this half adder, and then have be a little funky. Just make it work. Have that carry into that half adder. Just go with that and say it's good. What happens to the carry from this half adder?
You want to OR it with the carry from that.
Ah, so we want to have an OR out here. Just roll with it. Roll with it. I'm going to slam you right into the wall. Okay, where do you want your OR?
The two carries?
All right, so we have our first carry. Well, you want the carry from this guy.
Yeah.
And what am I ORing that with?
Now you're making me dumb myself.
All right, hold on. We'll put this guy back. So we had two half adders sitting next to each other. Help me build a full adder with two half adders. And then we're going to see what we can remove.
You want the carries from both the half hours. Yes.
Okay, well,
Stand by that one.
what's my input to the second half adder?
The result from the first one.
Okay, so this is our carry, this is our result. Okay, so we're going to feed the result into our second half adder.
Yeah.
Okay. And then you want to feed the, let's say that's good enough.
The result from the next one is just your actual result.
So this guy's the answer.
Yeah.
Comes out the space.
And then you want the two carries ORed together.
Yeah. And then that's your carry.
That's my carry. Steal that guy. Okay, so now we've written it in an abstracted way with half adder sitting there. How can that be simplified? So the challenge is, how do you create a full adder without using two half adders and be more efficient? Not just say, well, they're both 6 gates, so just roll with it.
Actually, it's 5. What's all?
You have to.
Remember, you have all the primitives available to you. Get all these guys. Except exclusive NOR. It doesn't exist. All right, let's take 10 minutes. We'll come back for the punchline, then we're going to talk about subtractors.